Everything you have ever seen, every star in the night sky, every planet, every galaxy, even your own body, is made of matter, visible matter, atoms, particles, light. But what if all of that is only a tiny fraction of what actually exists? Modern cosmology has revealed something astonishing. Everything we can see makes up less than 5% of the universe. The rest is invisible, not hidden behind dust, not too far away to detect, but fundamentally unseen, undetectable by ordinary means. This mysterious substance is known as dark matter. We cannot see it, we cannot touch it, we cannot observe it directly, and yet its presence is everywhere, because without it, the universe as we know it could not exist. The first hint of dark matter came from unexpected observations. In the early 20th century, astronomers began studying how galaxies rotate. They expected that stars farther from the center of a galaxy would move more slowly, just as planets in our solar system orbit more slowly the farther they are from the sun. But when they measured the motions of stars in distant galaxies, they found something strange. Stars at the edge were moving just as fast as those near the center, in some cases, even faster. According to the law of gravity, this should not be possible. Galaxies should not be able to hold themselves together at those speeds. They should fly apart, but they don't. Something unseen must be providing additional gravitational pull, something massive, something invisible. Later observation revealed even more evidence. Entire clusters of galaxies were moving as if they contained far more mass than we could account for. Light alone could not explain their motion. There had to be something else, something hidden. Over time, this invisible component became one of the central mysteries of modern physics. Dark matter is not just a small correction to our model. It dominates them. It makes up about 85% of all matter in the universe. It forms vast halos around galaxies. It shapes the large-scale structure of the cosmos. It acts as an invisible scaffolding upon which galaxies are built, and yet we still do not know what it is. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiations. The only reasons we know it exists is because of its gravitational effect. It bends light. It influences motion. It shapes the universe, but it remains hidden. And this raises a profound question. If most of the universe is made of something we cannot see, then how much of reality we are truly observing? Because the galaxy we admire, the star we study, the cosmic structure we map, may only be the visible surface of something much larger, something deeper, something invisible, a hidden universe, holding everything together. To understand why dark matter is necessary, we must first understand how galaxies are supposed to behave. At the most basic level, galaxies are held together by gravity. Stars orbit the center of a galaxy just as planets orbit a star. The gravitational pull of all the mass within the galaxy determine how fast those stars move. This relationship is well understood. In a system like our solar system, most of the mass is concentrated at the center, in the sun. As a result, planets farther away move more slowly. This is described by classical gravitational law and confirmed by observation. For a long time, astronomers assumed that galaxies would behave in a similar way. Most of their mass, they believed, was concentrated in a bright central region where most of the stars are located. So, stars at the outer edge should orbit more slowly than those closer to the center. But when astronomers began measuring these motions in detail, they found something completely unexpected. Instead of slowing down, stars in the outer regions of galaxy were moving at nearly constant speed. This pattern is known as a galaxy rotation curve, and the observed curve does not match theoretical predictions. They were flat, even far beyond the visible edge of the galaxy. This was one of the first major clues that something was missing, because if only visible matter were present, the gravitational pull would not be strong enough to keep those fast-moving stars in orbit. The galaxy should be unstable. Stars should escape into intergalactic space, but they do not, which means there must be additional mass that we cannot see. To explain this, scientists proposed that galaxies are embedded within massive, invisible halos. These halos extend far beyond the visible regions of the galaxy, and they contain far more mass than all the stars combined. These are known as dark matter halos. Within this framework, galaxies are not isolated systems of visible stars. They are structures built inside vast, invisible clouds of matter. The stars we see are only the luminous core. The true mass of the galaxy lies hidden. But the evidence does not stop there. Another powerful confirmation comes from the way light behaves in the presence of gravity. According to relativity, massive objects bend the path of light. This effect is known as gravitational lensing. When astronomers observe distant galaxies through massive clusters, they often see distorted or stretched images, arcs of light, multiple images of the same object. By analyzing the distortion, scientists can map the distributions of mass in the cluster. And what they find is striking. The amount of mass required to produce the observed lensing is far greater than what we can be accounted for by visible matter alone. Once again, something invisible is contributing most of the mass. On even larger scale, dark matter plays a crucial role in the formations of structure. In the early universe, tiny fluctuations in density, visible in the cosmic microwave background, began to grow under the influence of gravity. But ordinary matter alone would not have been able to form galaxies quickly enough. There simply wasn't enough time. Dark matter provides the solution. Because it does not interact with light, it began clumping together earlier than ordinary matter. It formed dense regions that acted as gravitational seat. Ordinary matter then fell into these regions, forming stars and galaxies. In this way, dark matter shaped the entire large-scale structure of the universe. The vast cosmic web of filament and clusters that spanned billions of light years. Without dark matter, that structure would not exist. So, while we cannot see it, its effects are everywhere. In the motion of stars, in the bending of light, in the formation of galaxies, and in the structure of the universe itself. Dark matter is not just an addition to our model, it's essential to them, and yet we still do not know what is E. By now, the evidence for dark matter seems overwhelming. Galaxies rotate too fast. Light bends more than it should. Cosmic structure form in ways that visible matter alone cannot explain. All signs point to the existence of something unseen. And yet, there is a problem. Despite decades of research, dark matter has never been directly detected. We have never observed a dark matter particle, never captured it in a detector, never measured it in a laboratory. All we have are its gravitational effect. This creates a fundamental tension because in science, the most convincing discoveries are those that can be directly observed or experimentally confirmed. Dark matter, so far, exists only indirectly. In the motions of stars, in the bending of light, in the structure of the universe. This has led some scientists to ask a bold question. What if dark matter does not exist at all? What if the problem is not missing matter, but our understanding of gravity? One alternative idea is known as modified Newtonian dynamics or MOND. Instead of adding visible matter, MOND modified the law of gravity as very low acceleration. Under this theory, the anticipated rotation curve of galaxies could be explained without dark matter. At first, MOND appeared promising. It successfully explained certain galactic observations, but when applied to larger scale, such as galaxy cluster and the structure of the universe, it struggled to account for all the data. Dark matter still provides a more consistent explanation, but Even within the dark matter framework, there are unresolved issues. For example, simulations of dark matter predict certain structure in galaxies that are not always observed. Some galaxies appear to have less dense center than expected. Others show distributions that do not perfectly match theoretical model. These discrepancies are small, but significant. They suggest that our understanding of dark matter may not be complete. Another mystery lies in its nature. If dark matter is made of particles, what kind of a particle are they? They do not interact with light. They do not seem to interact strongly with ordinary matter, which made them incredibly difficult to detect. Experiments around the world have been researching for these particles for decades, using highly sensitive detectors buried deep underground, shielding from cosmic radiation, waiting for even the faintest interaction. So far, nothing definitive has been found. This leaves us in a strange position. We are almost certain that dark matter exists, and yet we have never seen it, never touched it, never identified what it is made of. This is one of the most compelling mysteries in modern science because it forces us to confront a fundamental possibility that most of the universe is made of something we do not understand, or that the laws we use to describe the universe are incomplete. Either way, there is a gap in our knowledge, a crack in a system, and somewhere within that crack may lie the answer. If dark matter cannot be seen, how do you study it? This question had driven decades of research across astronomy, particle physics, and cosmology, because while dark matter does not emit light, it leaves traces, subtle signal, clues that scientists can follow. One of the most powerful methods is the study of gravitational lensing. When light from a distant galaxy passes near a massive object, its path is bent. This can create distorted image, arc, or even multiple copies of the same galaxy. By analyzing the distortion, astronomers can map the distributions of mass, both visible and invisible. What they consistently find is that most of the mass in galaxy and cluster is not visible. It exists in extended halos surrounding them. But gravitational lensing does more than confirm the presence of dark matter. It reveals its structure, its distribution, and how it interacts, or more precisely, how it does not interact with ordinary matter. One of the most striking examples comes from a system known as the bullet cluster. In this collisions between two galaxy clusters, astronomers observed something extraordinary. The visible matter, primarily hot gas, was slowed down and concentrated in the center, but the majority of the mass traced through gravitational lensing passed straight through unaffected, separated from the visible matter. This provided strong evidence that dark matter is not just an effect of modified gravity. It behaves like a distinct component, something that can move independently, something that does not interact strongly with ordinary matter. Beyond astronomy, scientists have also attempted to detect dark matter directly. If dark matter is made of particles, then those particles may occasionally interact with ordinary matter, even if very rarely. To detect such interaction, researchers have built highly sensitive detectors deep underground, shielded from cosmic radiations and background noise. One class of experiments searches for hypothetical particles known as WIMPs. These particles are predicted by some extensions of particle physics. They will have mass, they will interact through gravity, and they might occasionally collide with atomic nuclei. If such a collision occurs, it could produce a tiny flash of light or a small amount of energy, detectable under the right condition. So far, however, these experiments have not produced a definite signal, which had led scientists to consider other possibilities. Another candidate is the oxygen. Oxygens are much lighter than WIMPs, and they would interact even more weakly with ordinary matter. Detecting them required different techniques, often involving strong magnetic field and highly sensitive instruments. These searches are ongoing, and like the search for WIMPs, they have yet to produce conclusive results. At the same time, particle accelerators such as the Large Hadron Collider are exploring whether dark matter particles can be created in high-energy collision. If such particles are produced, they would not be detected directly. Instead, their presence would be inferred from missing energy and momentum. But so far, no clear evidence has emerged. This has led to a growing realization: dark matter may not be simple. It may not consist of a single type of particle. It may be part of a richer, more complex sector of physics that we have yet to uncover. Or it may interact in ways we do not yet understand. Despite the challenges, the search continues. New experiments, more sensitive detectors, more precise observations, each one narrowing the possibility, each one bringing us closer to an answer. Because dark matter is not just a missing piece of the puzzle, it is the dominant form of matter in the universe. Understanding it means understanding how galaxies form, how structure evolve, and how the universe itself is held together. And somewhere, hidden within the faint signal we are only beginning to detect, may lie the key to one of the greatest mysteries in science. After decades of searching, Scientists have arrived at a remarkable conclusion. We do not yet know what dark matter is, but we have a growing idea of what it might be, and just as importantly, what it is not. First, dark matter is not ordinary matter that we simply cannot see. It is not made of atom, not composed of proton, neutron, and electron. If it were, we would detect it through light, either by emission, absorption, and scattering. But dark matter does none of these. It does not interact with the electromagnetic force, which means it is fundamentally different from everything we are familiar with. It is also not simply black hole, dust, or faint star. These objects, while different to observe, still interact with light in measurable way, and survey of the universe had ruled out enough of them to account for the missing mass. Dark matter must be something else entirely, something new. For many years, the most popular explanation has been a class of particles known as WIMPs. These particles would have mass. They would interact through gravity, but only very weakly with ordinary matter. In the early universe, WIMPs could have formed naturally in the right abundance to explain the amount of dark matter we observe today. This idea, sometimes called the WIMP miracle, made them an attractive candidate. But despite extensive research, WIMPs have not yet been detected. This does not rule them out, but it has forced scientists to broaden their search. Another leading candidate is the axions. Axions are extremely light particles, far lighter than any particle we have directly observed. They were originally proposed to solve the problem in quantum physics, but they also have properties that make them suitable as dark matter. If axions exist, they could form a vast, diffuse field throughout the universe. Unlike WIMPs, which behave like individual particles, axions may behave more like a wave, a continuous background influencing matter through gravity. Experiments are now searching for subtle signals that could reveal their presence. But dark matter may be even more complex than a single particle. Some theories suggest that it could consist of an entire hidden sector, a parallel set of particles and forces that interact very weakly with our own. In this view, dark matter is not just one thing, it is the whole unseen world, with its own structure, its own interaction, its own physics. If true, this would mean that most of the universe is not just invisible, but fundamentally different from anything we know. Regardless of its exact nature, one thing is clear: dark matter plays a crucial role in shaping the cosmos. In the early universe, is begun to clump together under gravity, forming dense regions long before ordinary matter could. These regions acted as gravitational seed, pulling in gas, forming star, building galaxy. Without dark matter, this process would have been far slower, possibly too slow to form the structures we see today. In this sense, dark matter is not just present in the universe, it is essential to it. It is the invisible framework upon which everything else is built, the scaffolding of the cosmic web. And yet, for all we have learned, the true nature of dark matter remains unknown. We know how it behaves, we know how it influences the universe, but we do not know what it is. This places dark matter in a unique position in science. Is one of the most well-supported ideas in cosmology, and one of the least understood. It is both established and mysterious, unknown, and that is what makes it so compelling. Because hiding something this invisible substance may be clues to new physics, new particles, new forces, perhaps even a deeper understanding of reality itself. If dark matter truly makes up the majority of matter in the universe, then everything we see, everything we know, is only a small fraction of reality. This is not just a scientific detail, it is a profound shift in perspective, because for most of human history, we assume that what we could observe define what exists. Star, planet, galaxy, these were the building block of the universe, but now we know what they are: only the visible surface, a thin layer on top of something much larger, something hidden, something we cannot directly perceive. This raises an unsettling question. If most of the universe is invisible, how much of reality are we actually experiencing? Because dark matter is not rare, it is everywhere. It's throughout galaxy. It's filled the space between them. It's formed massive halos that extend far beyond the visible edge of cosmic structure. In fact, our own galaxy, the Milky Way, is embedded within a vast halo of dark matter, a halo that contains far more mass than all the stars combined, and yet we cannot see it, we cannot feel it, we pass through it constantly without noticing. This means that at any given moment, we are moving through a sea of invisible matter, a hidden component of the universe that coexists with everything we observe. But there is something even more profound. Dark matter does not just exist alongside visible matter, it controls it. The formations of galaxies, the motions of stars, the structure of the cosmic web, all are shaped by dark matter. In a sense, the visible universe is a byproduct, a secondary layer built on top of an invisible foundation. This reserves our intuitive understanding of reality. We tend to think of the visible as primary, the unseen as secondary, but in the case of the universe, it is the opposite. The invisible dominate, and this leads to a deeper implication. If dark matter is fundamentally different from ordinary matter, then most of the universe is made of something we do not understand, something that does not follow the same rules as the matter we are familiar with. This suggests that our current understanding of physics is incomplete, because the standard model of particle physics, one of the most successful theories ever developed, does not include dark matter. It cannot explain it, which means there must be new particles, new forces, or new principles we have yet to discover. And if that is true, then dark matter is not just a missing piece of the puzzle, it is a doorway to new physics, to a deeper understanding of the universe. But there is also a more unsettling possibility that dark matter is not just different, but entirely separate. That it may form structure we cannot see, interact in way we cannot detect, perhaps even give rise to phenomena we have not yet imagined. A hidden universe within our own, coexisting with everything we observe, but remaining completely invisible. This idea challenges our perceptions of reality, because it suggests that what we experience is not the full picture, not even close. We are observing only small fractions of what exists, and the majority remain hidden, unknown, unexplored. There's also the questions of detection. If dark matter interacts so weakly with ordinary matter, will we ever be able to observe it directly, or will it remain forever inferred, a presence known only through its effect? This uncertainty is part of what makes dark matter so compelling. It is both real and elusive. Every galaxy, every cluster, every large-scale structure in the universe bears its signature, and yet we have never seen it, never identified it, never fully understood it. And perhaps the most profound implication in this, the universe is not just stranger than we imagine. It is dominated by something we have yet to comprehend, something that holds everything together while remaining completely invisible. For decades, dark matter has remained one of the greatest unsolved mysteries in science. We know it exists, we know it shapes the universe, but we do not know what it is. And that is about to change, because a new generation of experiment is pushing the limit of what we can observe. Deep underground, far from the noise of cosmic radiation, scientists have built some of the most sensitive detectors ever created. Vast chambers filled with ultra-pure material, designed to detect the faintest possible interaction. a single collision between a dark matter particle and an atomic nucleus, a tiny flash of light, a small burst of energy, signal to software that they can easily be mistaken for noise. And yet, within that noise may lie the first direct evidence of dark matter. At the same time, particle physicists are searching for answers using the most powerful machine ever built, the Large Hadron Collider, accelerate particles to near the speed of light and collide them at extremely high energies. If dark matter particles can be created in these collisions, they would escape detection, but their presence would be inferred through missing energy, through imbalance in the data, clue that something invisible has been produced. So far, no definitive signal have been found, but the search continues. With each new dataset, scientists refine their model, narrowing the range of possibility, eliminating what dark matter is not, and getting closer to what it might be. Meanwhile, astronomers are mapping the universe with increasing precision. New telescopes are observing billions of galaxies, tracing the distributions of matter across cosmic scale. Projects like the Very Rubin Observatory will create the most detailed map of the universe ever produced. By tracking how galaxies move and how light bends around massive structures, scientists can refine our understanding of dark matter distribution and perhaps uncover subtle clues about its nature. There are also experiments focused specifically on detecting alternative candidates, sensitive instruments searching for X-ray signals, using powerful magnetic field, resonant cavities, and quantum sensors. These experiments are exploring entirely new regions of possibility because dark matter may not behave like anything we have seen before, and perhaps the most exciting possibility is that the answer may come from an unexpected direction, a signal that does not fit existing model, an anomaly that forces us to rethink our assumption, a discovery that reveals something entirely new, because that is how science often progresses, not through confirming what we expected, but through discovering what we do not. The search of dark matter is not just about identifying a new particle. It is about understanding the fundamental nature of the universe. It is about answering one of the deepest questions in science. What if the universe made up? And as we continue to build more powerful instruments, more sensitive detector, and more precise model, we move closer to an answer that may transform our understanding of reality itself. When we look up at the night sky, we see a universe filled with light, stars burning across the darkness, galaxies stretching across unimaginable distances, a cosmos that felt vast but visible, Understandable, but that vision is incomplete because everything we see, every star, every planet, every galaxy, is only a small fraction of what truly exists. The rest is invisible. The dark matter that's surrounding us shaped the universe and hold it together. It does not shine, it does not reflect, it does not interact with light in any way we can detect. And yet, without it, galaxies would not exist, stars would not form, the cosmic structure we observe would fall apart. In a sense, the visible universe is only the surface, a thin layer of light resting on a vast, unseen foundation, a hidden framework that defines the structure of everything. And this realization changes how we see reality because it means that what we experience, what we observe, is not the full picture, not even close. We are living in a universe dominated by something we cannot see, something we cannot directly measure, something we do not yet understand, and yet it is everywhere. It surrounds us, it passes through us, it shapes the motions of galaxies and the evolutions of the cosmos, all without revealing itself. This is one of the most profound discoveries in science, not because of what it tells us, but because of what is implied. What is the universe is far more complex than our senses can perceive. Thus, reality extends beyond what we can directly observe. Thus, there are layers of existence hidden beneath the surface, and dark matter is just one of them, because if most of the universe is invisible, what else might be hidden? What other forces, particles, or structure might exist beyond our current understanding? What other discoveries are waiting to be made? The search for dark matter is not just about solving a scientific mystery. It is about expanding the boundary of human knowledge, about pushing beyond what we can see and into what we can only infer. It is a reminder that the universe is not limited by our perception, that it operates on scale and principle that we are only beginning to understand, and that the journey of discovery is far from over, because somewhere in the darkness, in the vast, invisible structure of the cosmos, lie an answer what could reshape our understanding of physics, of matter, of reality itself, and perhaps of our place within it.